In the name of Almighty God, I am Hassan Kashi, and today I want to talk about further examples about angular momentum. There are many additional examples of the method presented in this section. We show a few common examples. The basic unifying feature of all examples in this section is that the behavior of the system can be described with a system of second order linear ordinary differential equations with constant coefficients. Now I'm going to go through the pendulums. In the limit of small displacements, the equation of motion of a pendulum of length L is described by simple harmonic motion. The full equation of motion for a pendulum with angular displacement theta is see the problem 4 in section 1.5.4. And now we have a formula ml theta zegon is equal to minus mg sinus theta. For a small displacement, this becomes mx zegon is equal to minus mgx divided by L based on the equation 1.46, which describes simple harmonic motion of angular frequency. The angular frequency equation based on the equation in 1.47 is omega is equal to a square root of g divided by n. A similar equation holds for an extended object of mass m swinging on a massless rod of length r which has moment of inertia I about the pivot. More precisely, r is the distance between the center of mass of the object and the pivot. The oscillation frequency is derived using Lagrangian mechanics is now omega is equal to a square root mgr divided by r based on the equation 1.48, which is easy to remember using dimensional analysis once you know the equation 1.47. Now I want to go through another example, which is circuits. The structure of a differential equations describing damped and driven oscillation is identical to the differential equations describing electrical circuits under the replacement in the table 1.1. All differentiation and differential equations remains perfectly valid for electrical systems after these substitutions, with the technical caveat that the quantities in the table refer to the effective quantities for the whole circuit or system, not individual circuit elements or springs. This shouldn't be too surprising since while one can add resistors in series or in parallel, it doesn't make much sense to add damping resistance in parallel. In particular, while it is true that 1 divided by chi equilibrium is equal to C equilibrium, one cannot just replace all individual capacitors by springs. Thought there is a simple rule for equivalent spring constants for springs in series and parallel that mirrors the rule for capacitors. See below for more details. Now I want to go through another example, parallel and series spring. Pursuing the electrical analogy, we can consider springs attached to a block of mass M in both parallel and series configurations. See the example 1.30. Now I'm going to go through the example 1.30. When the springs are in parallel, figure 1.16 left, the equation of motion is mx second is equal to minus chi x minus chi x is equal to minus 2 times of chi x. So the effective spring constant, the sum of the two spring constant, K plus K is equal to 2K. When the springs are in series, figure 1.16 right, the situation is slightly more complicated. Call the displacement of the massless joint between the springs x1 and call the displacement of the block x2 to determine equations of motion. We can use a trick. Pretend a very small mass is attached to the joint between the two springs. In this case, we just have a two spring system very similar to the one we already solved in section 1.71.1. Simply copying down the first equation of motion and sending the small mass to 0 gives 0 is equal to minus chi x1 minus chi multiplied by x1 minus x2. Notice that this is no longer a differential equation but an algebraic constraint equation where x1 is equal to x2 divided by 2. This enforces the condition that there must be zero force acting on the joint between springs. Otherwise, since the joint is massless, the acceleration would be infinite. The block just experiences a force due to the spring touching it, so its equation of motion is mx second 2 is equal to minus car x1 minus x2. Plugging in the constraint, we get mx second 2 is equal to minus car divided by 2x2, giving an effective spring constant of car divided by 2. And you can see the figure 1.16, which is springs in series and parallel. You see that we have a springs in series with a car constant, and here is a parallel. Table 1.5 correspondence of quantities in analogy between electrical and mechanical systems. Now I want to call the mechanical systems in the first column. The second column, I want to go through the circuit system. X as a displacement, we have Q charge, X current as velocity, I current, M mass, L inductance, D damping resistance or electrical resistance, 1 divided by car spring stiffness, which is C capacitance, F amplitude of driving force, V amplitude of driving voltage. If you go through the derivation example 1.13, which two different spring constant car1 and car2, you can prove to yourself that the rule of for computing equivalent spring constants is 1 divided by equilibrium is equal to 1 divided by car1 plus 1 divided by car2. The same as the rule for computing equivalent acceptances for capacitors is series. 1 divided by capacitance equilibrium is equal to 1 divided by C1 plus 1 divided by C2. This leads to a subtle pitfall. The electrical analogy of our series spring system above is two capacitors in series. If we were to replace each spring car by a capacitor C, the rule of table 1.1 gives 1 divided by car, which is going through the C. But the equivalent capacitance of this system is C divided by 2, and the equivalent spring constant is car divided by 2. So the rule is car divided by car equilibrium, which has a tendency to go to the C equilibrium, becomes 2 divided by car go through the C divided by 2, or 1 divided by car is going to C divided by 4. So the electrical mechanical analogy is not as simple as just replacing 1 divided by car by the C everywhere in the circuit. To keep things straight, it's best to remember the two rules as logically distinct. The first rule, the rule for adding springs, in series and parallel, is the same as adding capacitors C in series and parallel. The electrical analogy to a mechanical system which equivalent spring stiffness, divided by equilibrium is an equivalent capacitors C equilibrium. Now I want to go through another section 1.8 fluid mechanics. In general physics course, fluid dynamics problems typically appear only in two simple forms. The first is in applications of Bernoulli's principle, essentially a reformulation of conservation of energy. The second uses the concept of buoyant forces. 1.8.1 Bernoulli's principle: consider a fluid that is traveling through some pipe. The pipe may go up and down and it may change diameter. Regardless, the following quantity is constant along a streamline of the fluid moving through the pipe: V to the power of 2 divided by 2 plus Gz plus rho P divided by rho is equal to constant based on the equation 1.49, where V is the velocity of fluid. G is the gravitational acceleration. Z is the height of point along the streamline. Rho is the pressure. P is the pressure and rho is the density of the fluid. Nearly all common fluids are incompressible in the sense that rho is the constant for any reasonable range of pressure P. You can remember this equation by noting its relation to conservation of energy. The first term is a form of kinetic energy, the second term is a form of gravitational potential energy, and the third term is an energy associated with pressure. Since the first two terms are just the unusual kinetic and potential energy terms with the mass divided out, the units of the constant on the right hand side of 1.49 must be energy per unit mass, a fact that can help you remember the form of the third term. Problems involving Bernoulli's principle typically just require applying this relation to two different points along a streamline, often in conjunction with a fluid conservation equation. From example 1.14, we can abstract the general strategy for problems involving Bernoulli's principle. Write down the Bernoulli equation at all relevant points for the system. Write down the equation for fluid conservation. Solve this equation for the described variables. Remember that not all problems need both the fluid conservation and the Bernoulli equation. If you need to know something about pressure, for example, you will certainly need Bernoulli, but maybe not the conservation equation. If you need to know something about the velocity of the fluid, the reverse could be true. Now I want to go to the 1.8.2 buoyant forces. Consider a block that floats in water. Figure 1.19. Obviously, the force of gravity pushes down on it, yet it doesn't sink. This is, of course, because of the buoyant force of the water that the block displaces. If the block displaces of a volume of V of water when it is floating, then the buoyant force pushing back up on it will be F is equal to rho Vg. And the equation is 1.52, where rho is the density of water or whatever fluid the block is floating in. You can think of this as the weight of the displaced water pushing up and the submerged object. The mass of the displaced water is rho v, and so its weight is rho vg. Problems involving floating and submerged blocks can usually be solved by simply assigning all forces as usual and then adding in the buoyant force which pushes upward on the object. For example, suppose you blow all the air out of your lungs and sink to the bottom of a pool. How much do you weigh underwater? Suppose you weigh 60 kilograms and your volume is 50 liter. You are displacing 50 kilograms of water, so there is about 500 newton of buoyant force pushing up on you, but your weight is 600 newton, so your net weight is only 100 newton. Quite an effective weight loss program. Thank you so much for watching my physics tutorial video until the end. Today is 13th of April 2026, 12:17 a.m.